So one of the most common data structures that we all use every single day is hash table. Every language has its own implementation and nomenclature for it. For example, Python calls it a dictionary while Java calls it a hash map. But the core idea remains the same. It holds pairs of keys and values and it supports constant time insertion, updation and deletion. But how are they implemented? What is its internal structure? In this video, we talk about what are hash tables, how are they structured internally, and we would lay a solid foundation to understand their constant time implementation. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page which is linked in the description down below. So if you are looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. So hash tables are indeed one of the most widely used data structures, and literally every single language has its own implementation and its own nomenclature for it. But really, is it just there to power our business use case? No. A really interesting fact about hash table is that it is also used as a building block for your language runtime. For example, you define a class has members and some functions, right? So when you do, let's say, a class box dot put, if you're doing something like this, someone like your language runtime needs to know this is the object, this is the method that it is being invoked, and execute this function for that. Right? This mapping is also, so in most languages, classes are also implemented as hash tables. Right? It's so widely used. Now imagine how many times are you using classes every single day. It's that common of an implementation. Second example for that is variable lookups. When you declare int a equal to 10 and then you are using, let's say, printing a, your language runtime needs to know that, hey, a needs to be print, which points to this location. So this is called as a symbol table, which is used basically like through which people do variable lookups, and that is also a hash table implementation. And this is the penetration of hash table. It is so widely used across not just your business use case, but also to power the language runtime. And basically that is what makes hash table one of the most important data structures out there. Right? So what are hash tables famous for? Hash tables are famous to store key value pairs. Right? You insert a key and then you insert, hey, this is the key, this is the value, and then when you would want that value, you would give it the key and you would get the value. Right? There's a simple use case of a hash table, but what it brilliantly does is it gives you constant time insertion, deletion and lookups, and this is what makes hash table super efficient, or it makes hash table special. Because imagine if it could not provide you constant time insertion, deletion and lookup, your fundamentals of your runtime, which is classes and symbol tables, they would be slow, which makes your entire language slow. That's why having a constant time implementation of near constant time implementation of hash table is super important. Right? So how are they constructed? So any hash table is constructed on top of or with these two basic foundational ideas. First of all, application key, like the first idea is where you map application key to a hash key. Right? So here the idea is the key that you are putting in a hash table, a language cannot restrict you on what key can you put in. Right? It would want to support as many type of keys as possible. For example, in this example, we say that apple is the key and value is 5. So apple is a string while value 5 is an integer. Right? So we need to store string as a key and some integer as a value. Our language or our hash table should be able to support that. But how would we store a string and then and the value against it, right? A language. And so basically that is where the concept of hashing comes in. So what you do is you need to somehow map an incoming key of any type to a wide range of integers, right? For example, in the range of 0 to n, it could be an entire integer range, let's say int 32. Like 2 raised to power 32 is what you can go for. But somehow use a hash function, use your favorite hash function to map your string to an integer. And then the second idea for constructing a hash table is to take this hash key and map it to a smaller range. You'd say, hey, we are doing string to int and again mapping int to int. We will come back on why the second step is more important, is really the crux of hash table implementation in some time. Right? Let's dive deep into the first step, where we say that application keys are mapped to hash keys. Like what and why? So pick any language. Pick any language. You would see that you are not allowed to put anything in the hash table. Like you can give string, tuples, integers, like some specific types are there that you are allowed to put as a key in a hash table. For example, in Python, you cannot put list into your hash table, as in the key of the hash table. Right? You can put it in the value, but you cannot do it on the key. So they are very specific about what could be a key for a hash table. So but obviously language would not want to, prevent you from inserting anything. So it needs a way to support it. That is where most languages, what it does is it gives you an ability to implement hash function. And now this hash function, like Java might have get code or hash, or basically function called a hash code. In Python, it is _ hash __. What it does, it expects you. So you can insert custom data types. Let's say you created a class and the object of it is you want to place it as a key in a hash table. Your class needs to implement a function called _ hash __, which returns an integer, right? And which would become your hash key. This is what you are supposed to write, right? And this is the whole idea of mapping your application keys into a hash key. So from any type that you have into a type or into integer, which then becomes an input for our second step. Right? And this typically, the function hash that I was talking about, that typically expects you to return an integer, which means in the range of 0 to 2 raised to power 32. Right? So this is what you would write. For some native data types like string, integers, you don't need to implement it. Like the language has its own implementation. But internally there has to be something that is converting your application level key through a hash function and converting into a hash key, which is then acting as the input for our second step, right? So this is the first step that we are doing, from application domain to mapping it to a wide integer domain through a hash function, right? That is first step. Then if we already have this, what could be a very naive implementation of a hash table? If you already have a way to map an application key into an integer, our very basic implementation of hash table could be through an array. Let's say we take a gigantic array right? We take an array where given a key, we pass it through the hash function. From this hash function, we get an integer. We use that integer as an index of our array and store the value at that location. For example, my key k gets indexed, or when I pass my key k through the hash function, I get value I, right? And the value I is the index at which I would be storing the value in this array, right? If I do this, what I get is I get constant time insertion, because for a hash key, for an application key, I'm computing the hash, going to that location, putting the value. Constant one insert, constant one update, constant one lookup, because everything is in memory, little constant one access is what you are getting, right? This sounds amazing, right? Why are we not implementing it then? The reason we are not doing, like, this approach would work, but only when n is small. When the range of the hash keys is small, then only you can do that. Otherwise, what would happen? Imagine your range of hash keys is entire integer range, which is 2 raised to power 32, 0 to 2 raised to power 32, which means that from application key, one of the values from 0 to 2 raised to power 32 would come out, right? So let's see how much of space would we require. If n is equal to 10, which means your array's length is equal to 10, or the number of possible hash keys is 10, the amount of storage you would require is 4 into 10 is equal to 40 bytes, because each slot of an array would be an integer where you are storing the reference of the value or something like that. So it would require you to store, it would require you 40 bytes. If it is 100, you would require 400 bytes. If it is 1 million keys that you would want to support, like that big of a range is what you are supporting, then that would be 4 MB. But imagine if you are expecting an int32 size, right? So from application key, you are converting it into a pure integer of range 2 raised to power 32. Then what you are doing, 2 raised to power 32 is more than 4 billion. And when you do it, 4 into 4 billion is equal to 16 GB. Imagine you would require 16 GB just to hold this array in memory, right? And given whatever it is hashing it to, you're going to that location and putting it. It seems definitely order one, insert, update and lookup, but the amount of storage required is huge. So when n is small, this approach is fine, but when n is your entire integer range, it's not good. Two key challenges that come over here. First of all, finding this big chunk of contiguous memory is tough, right? Because because when you allocate an array, it has to be a contiguous set of bytes that are allocated, and finding this big of a memory chunk is always difficult, right? So that is problem number one. Second is, even if we get that much of allocation, let's say you are mapping your application key to a hash key in the range of 0 to 2 raised to 32 and you are only inserting 5 keys, then you are wasting so much of space, right? So this is not space efficient. You are pre-allocating a massive space which is heavily underutilized. So that is where there has to be a better way to construct a hash table, which is where the second step comes in, which is really important, of mapping of hash key to a smaller range. So hear me out. If we are planning to store k keys in the hash table, so the total number of keys that we are planning to store in our hash table is k. K could be 5, 10, 15, 20, something. Then how big our array should be, right? Because if we are only planning to store k keys, our array should not be 2 raised to power 32. It's not practically possible. So that is where our array should be small. So let's say if that size is m, right? How big our holding array would be, that is m. So m should be in order of k. Like it should be just big enough to hold k keys. It should not be extraneously large, but it should not be small either. It should be somewhere that efficiently helps us put all the keys that we want in this holding array. And this is the crux of provisioning, of finding out the sweet spot of how big our array should be, and which is what varies almost all hash table implementations, right? So what we'll do is, in the second step, we take the hash key, which is in the range of integer 0 to 2 raised to power 32, and map it into a smaller range of 0 to m, where m is the length of the array and length of the array should be a function of the number of keys that you are holding, right? So this is the second step, and which is what now makes our hash table very efficient, right? So now let's say we are planning to store 4 keys in the hash table, so we can have a bin. So the holding array is called as a bin, and this bin could be of length 8. So instead of having 2 raised to 32 as the holding array, we can have just 8 because we are planning to store only 4 keys. And what we'll do is for every key, we would, every application key, let's say Apple, it first passed through the hash function, we get a hash key. Let's say for Apple, we get 127622179, some big number, right? We take this hash key and map it to a smaller range of, let's say, 0 to 8, right? Because your array length is 8. Let's say we got 0. So where does Apple sit? Apple go and sit in the holding array at index 0. Similarly, let's say we have banana. Banana, when I pass through the hash function in the first step, I get value 51962, again a random number. It gets indexed, and then when and this is the hash key. When I pass it through my second step and map it to a smaller range of 0 to 8, let's say I get 5. So this is another hash function that we are passing, right? So now we have 2 hash functions over here. First hash function converts application keys into a hash key, and second hash function converts hash key into a smaller range, right? So 0, 5, and let's say cat, hash key to 72, smaller range mapped to 3. So your cat goes and sits at index 3, while dog, when I hash it the first time, it gets 1962719 as my hash key. When I pass it to my second function, I get 7. So my dog sits at index 7. This would make our life so simple because now we are not needing to allocate a massive array. We are still getting constant time implementation, right? Because each element is almost uniformly distributed across this array. The array is just 8, it's just having 8 slots, so 4 8s are 32 bytes big. So it's not extraneously large. It's big enough to hold all of my keys, provide me a constant time lookup while ensuring that I am being efficient all the time, right? And this is why we need 2-step process, or any hash table implementation requires 2-step process. First, from application domain key to hash key, and second from hash key to a smaller range. Now, you'd say, hey, but Arpit, what if now I don't want to store 4 keys? Now let's say I want to store 12 keys. My language doesn't wait. My language is constantly accepting the keys that I'm writing. How is my language doing that? So that is where, when you're trying to add more keys, what your language internally or your hash table implementation internally does is it grows your bin. It grows this array. It changes m and changes it to m equal to 2 into m. So it makes this array double every time. And that is one of the implementation. You don't always have to make it 2x of what it holds, right? But that is one of the implementation. And when that happens, you are reallocating a big chunk of array, right? So let's say you had 8, and now let's say you exhausted the limit, and now you would want to add more to this array. So obviously this has to be an array. So what you do is you try to reallocate and then reindex all the keys into this new array, and that would require you to take a pause in accepting the writes that are coming in. And then you would, once you allocate a big chunk, you move all the existing keys, and then you start accepting other puts onto this hash table, right? And this is what happens internally, right? And this is okay because you are not doing very frequent allocation. Only when you are exceeding the number of keys that your existing bin can store, then only you are doubling the size, or not really doubling but increasing the size, right? And this is what you have to answer. This is what internals of hash table implementations are, right? So then why are we even hashing from the application domain key to integer? We get 2 very solid benefits of doing this, right? Because of the first step, what we are doing is we are simplifying our problem statement. Given that for any type, we are converting it into an integer of range 2 raised to power 32, now our problem statement becomes very simple, because this could be something that your end user provides or your business logic provides with hash functions and whatnot, right? And for us, the internals of hash table, our input is this integer that we are getting. And how we would want to map these big integer range into a smaller range is our efficiency coefficient of our hash table implementation. Like how well we do it, how well we distribute it, how well we provision it, and all of that is then on us to implement as part of hash table implementation. And this is why first step is very important, and that's why we are hashing the first set of application keys into a big integer range, and from this big integer range into a small integer range. Right? The second step is also like it also enables us to keep our hash table agnostic of what type we are storing, because at the end, given that you can support literally any object and get an integer value out of it, that becomes a hash key as their own implementation. So you created a custom class. Let's say you created a custom class, let's say car. You want to store car as a key in your hash table. So an object of a car as a key in the hash table. All you need to do is just implement the __ hash __ function, which returns you an integer. Right? Your user doesn't have to write multiple hash functions per se. All it does, it just returns an integer. And once you get this, it's up to you. You have abstracted out. Now your hash table implementation is working on only this integer range. So from 2 raised to 32, it needs to map to a smaller range of 0 to m. And this is what makes it super special. So you have abstracted out the complexities of supporting multiple types. Right? All your end user has to do is just provide you the hash function that spits out an integer for a given object. Done. Now for you as an hash table implementer, you have the key, you have the integer, you map it to whatever range you want, the way you are storing it onto the disk, right? And if your m resizes or if your bin array resizes, your end user does not, the end user is not getting affected at all. Your end user continues, like you never have to change the business logic of your code. What you do is from this integer range, you just change the hash function and how you are distributing and other kind of stuff over here. This is what we would be looking at into this series of hash table implementation. This is first video in this series where we are talking about hash tables, because this is such a fascinating data structure. In this series, I'm planning to go deeper into a lot of implementation details of hash table and planning it to implement in raw C language using arrays and a lot of super interesting insights around it. Right? So yeah, that's it. That's it for this video. I hope you found it amusing. I definitely did when I first stumbled it a few years back on needing of 2 levels of hash functions. That was a brilliant way of abstracting it out while ensuring efficiency. So I love that particular part and I wanted to share it with you. So in this series, we would go deeper into hash table implementation and we would have fun doing it. Nice. So yeah, that's it for this video. If you guys like this video, give this video a massive thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week and I'll see you in the next one. Thanks a ton.